Minsung Kim from the Nicolaus Copernicus University in Toronto. The title is Effective Equidistribution of Nilmanifolds. Please.
Thank you for the invitation. Thank you for coming to the seminar. Today I want to talk about the effective distributions for nilmanifolds. So before we start, I want to define what is the nilmanifold. So what is one leader or
Mini, oni wydaje mi się, że tak. Oni coś wiedzą? Oni mają to samo. Okej, może on to pisze. Oni mogą lepiej. Tak było w będę. Please continue.
So this means there exists
I'm sorry, could you speak a bit louder?
And also write
Speak louder.
okay, yeah.
and write larger.
And write louder.
All right. When we start with G, then we can calculate the commutator group, and then repeatedly we will arrive after the n step, and then if it is identity, then we call this an important. We also consider the lower series. Zero. So we also define the G1 G. And also in the same way we can place so we also call the step here is step n. The set is spice G O N. See some example for the example is Heisenberg. So Heisenberg algebra contains three elements, like x, y, and z. And these three elements satisfy for x and y, they all commute, but the other in this case we call community elements in so we can also write Heisenberg algebra in the following way. So we can write G as a set of elements in the strictly triangular matrix. Also, for in the group sense, we can also write 1, 1. Now we can define the new manifold. G the equivalent figure, and then we can consider its lattice. So G is equal. Then we define quotient of G by this lattice. And then actually we can find some, we can also find some structures. We can also consider commutators. And then this so we can quotient the group by this commutator. Organizations. Because if you have all the elements in the G, in the some first and right x1, and by breaking relations, it generates some other elements over there. So basically, we will quotient out all the elements in the lower level. So we only have elements in the first level, and then they also commute. That's why it's called organizations. And in the same way, you can also consider the lattice. And then is isomorphic to torus. So in the general manifold, you can view the manifold as a with the base torus, and it also has a total fibers, and it keeps having some total fibers in such a way. And also we saw that the step is the smallest number, and this structure is repeated up to n stage. And but we also see, you can also see there is also projections from the base torus. So when we only consider first level, then we can always project to the base torus. So now here, let me define Nilflows. No parameters actually. So this is generated in by so here this x is the point on the nilmanifold, and x is element in the algebra. So given point on the x, and then we will consider the one parameter circle generated by the element of the real as a vector field. So this one is defined. So Nilflows is defined in this way. And we can, from this point of view, we can also see on M given Nilflows, we can also find its projection on the base torus. Right? Sign. We can just project the flow of the base torus, and then now we can talk about some ergodicity for the Nilflows. So the flow of the Nilflows.
Understand something.
Yes.
Same x here. Why x? No, relative. Here it's fine. X.
So this is a small x, and this one is x.
Ah, this is big x.
Yeah, yeah.
It's a different x.
Yeah.
This is the linear.
Yeah,
Okay, so we start from a point. So small x is the point.
Yes, yes.
We start from small x and go along capital X.
Yes. Go along with the
Different x.
The different.
Confused.
So yes, so Nilflow is and also minimal, and we can only minimal. If the projected flow is irrational, if the flow is active,
That is the same as on the brain.
yes, yes.
So by coming.
Yes, and then we can define the projected flow on the base torus. And when the frequency is irrationally independent. And then we can, and this is if and only if the whole Nilflows is uniquely ergodic.
This is about projected flow from the first commutator, and then you can continue projecting. No, that's the biggest. That goes down to this.
Yes, we only consider the base torus.
That's actually a theorem by Leon Leibniz. It's a theorem by Leon Leibniz.
I think it was like almost, yes, in the 60s.
This fact that
Yeah, this is
latent is not just like it's not, it's a theorem.
Yeah, yeah.
So can you read again the theorem?
So Nilflows is uniquely ergodic if and only is minimal, and if and only the projected flow on the base torus is irrational.
You can check it on the base flow, that's the point. On the
Yes.
base is just this ratio or the last stage of.
This is not the last stage. It's
What is it? This is the text. No, because the last stage of the tower is also close.
yes, yes.
That's why I missed. Yeah.
Yeah, yeah. You only consider the first one.
You just
The
take
base.
first ratio.
Yes.
Factor. But you know, this sequence is decreasing, right? So it's you do G divided by the biggest one, the parallelization. So you get that in the geometrical, you get down to the base. So it means that this is what is written. Yes.
Yeah, so basically we push out by the commutator. So there is no other elements. So it's more or less the step size is one. So yeah, new. And also Nilflows. because it has a polar vectors. So therefore, their mixing but it's possible to obtain some mixing for time changes. It's possible. Well, just for that. They prove the time changes, some time changes on the general manifold can be a mixing. So mixing for time changes. This is only for the Heisenberg.
Time changes. More.
Yeah, vertical mixing.
But for what time changes? Some or
Some
typical time changes?
I think it's some dense sets or yeah.
General, if you have a
Yes.
system which is not mixing,
Yes.
but has some time change which is mixing. Does this say something in general? Because I would imagine, of course, there are systems that no matter how you time change them, they are never mixing, right?
Like they are not.
But I think ergodicity doesn't change if matter can change. But you mean for the mixing, I mean, for example, for torus case, if you change the time, I think it's possible to.
Yeah, right, of course.
Yeah,
It's
yeah.
all from this.
But that's not ergodic time change.
No, it's not there. It's not ergodic. Yeah.
Okay, and I think it's ergodic and no time change is mixing. No, it's just interesting phenomenon.
Let's say it's not ergodic, then we cannot change.
Yeah, it's not ergodic. There's no chance. Yes.
Yes, of course, because of the instrument.
So now we assume the flow is uniquely ergodic, and if flow is uniquely ergodic, then we can consider the difference between the time averages and the space. So as t tends to infinity, the difference tends to 0. There is just some more. So effective equidistributions means
This time, it's unique ergodicity.
yes, we assume uniquely ergodicity. So
The ergodic average.
yeah,
Forever.
yes, forever yes. The effective equidistributions means we want to find the bound for these two differences. So when we fix Then we want to find how this difference, how fast does it converges to 0? Now let's introduce some more results. First result is and they proved the basically they proved is for so we just saw the structure of real manifold, and this bound is just for some delta. I mean, we know
Does find this time change? Or
no, this is just flow.
what?
This is uniquely ergodic.
This is flow. Okay.
For flow, yes. And then they proved, but this exponent doesn't show any information about the structure of the manifold. Wherever X is.
Capital O of what?
It's t to the minus delta. Delta is between 0 and 1. Yeah. Flaminio-Forni, they also so this one is only for Heisenberg. Then this bound is actually its optimal. Later, they also proved the same result, and yes, same result, but they used some different method. So by the method of Buffetto, he could define some cocycle called Buffetto cocycle or Buffetto functional, and then they also proved the split statement using some different methods. And then also their result is some limit theorem for ergodic integral.
Of course, natural question would be whether it cannot get rid of epsilon. No, probably not.
Yes, but actually that one depends on the choosing Diophantine conditions. So we need some Diophantine conditions, but if it's bounded type, then we can remove epsilon. Yes. But yeah. But for general, for full measure, we have to get some provided, yes.
But did you say that in the third paper there was also a convergence? Is that I couldn't hear what you said.
So they also proved that this statement, I mean the bound is t to the minus f plus epsilon. But statement is a little bit different. They just they prove approximated by some functionals. But this type of argument still gives the same bound. So this one is called Buffetto cycle. So it's just using different methods. And once you can define such functional, then we can also prove some type of limit theorems.
Artyom, are you recording this?
Yes.
No, maybe you should.
Yes, recording.
Not the host. Atom is the host.
He is the host. Okay. So you are recording.
Yes. Sorry, I couldn't hear.
Okay.
Yes. And also the very reason was we also prove the same thing, right? But they use some different method as well. So they use the analytic method from hyperbolic theories. And this is the hyperbolic dimensions. In this case, actually the difference is they couldn't prove for the any general some alpha, I mean the frequencies. So they only prove some special types.
Yes, so for this, he goes is whatever.
No, it's Heisenberg.
Or is the Heisenberg?
Also for Heisenberg.
So
This is for Heisenberg.
yes, this is for the Heisenberg.
But you are referring now to an additional parameter which you have not defined. You are talking about some alpha or some Diophilic condition. It's not.
Yes, I didn't mention. Yes.
Yes, so I don't understand the statement when you say it's only for some alpha. What do you mean by that?
So alpha means. So we will consider the flow, but I would say the alpha. So here alpha means it's not only a single element, it will be
Family.
no, it's not family. This alpha will be more or less like x alpha 1, x1, alpha 2, x2. It could be some linear combinations. 4 elements in the first level. It's not only choosing one element. So from n to p, and then we also need some Diophantine conditions on the base torus. So
What is the you are talking about the irrational rotation?
Irrational rotation, yes.
And now
yes.
you are talking about condition on class.
Irrational rotation, yes.
And they need an additional condition.
Yes, yes.
Ah.
Exactly. Yes. And then, yes. They also put some general type of nilmanifold. So in this case, it was only Heisenberg, but they also consider this more. And my work is for strictly let's see what is the quasi-abelian and triangle. So quasi-abelian we have one element x and there's another element y. And then x, actually I will write just y1 and x and the bracket with x y plus 1. So x and y1 will give y2, and x and y2 will give y3. And we will stop at the end. So after n, it will be 0. So this one is a step n. Step n is important to the algebra. And you can see between yi y3. So that's why it's called quasi-abelian. So for this part is abelian, but we have a single extra element, x. And also triangular is we have x1, 2, xn in the first level in the generator. And then by commutations, I will write x1 1 and xn 1. And by commutations, it also gives some element x1 1. By commutations, it only gives just one element at the last stage. So for the quasi-abelian, was change 2 over k times this one. And for triangular, it's 1/3. And k plus k times k plus 1. And k plus 1 plus epsilon. So quasi-abelian case and triangular case is very different from the Heisenberg because the whole dimension becomes very large.
But wait, what is K?
K is the right? K is the step size.
But wait, we saw that the two-step Heisenberg is quasi-abelian.
Yes, that is very special case.
But already the higher, of course, they are not. They are not.
So
The higher case of Heisenberg.
yes, yes. Okay. You can think like generalized Heisenberg. So actually this form is related to the structure of the algebra. So from here you can see y1, y2 up to yk, and then you can assign some numbers like 1, 2, 3, and so on. Also for triangular, you can think like 1 and 2, 2, and 3, 3, 3. So we will assign some weights on each algebra. And then this weight will determine the exponent for ergodic, speed of ergodic averages.
Is this optimal?
No, this is very far from optimal. Yeah. So now, yes, some questions. So here's the question. So you want to find some general statement for finding the boundary difference of time and space averages.
I'm not sure I understood the definition of triangular.
Sorry?
I'm not sure I understood the definition of triangular.
Yeah.
When you wrote like this, what do you mean?
So I just mean it's on the triangular matrix. Triangular matrix. So we can think like
Okay, so that is just a triangular matrix.
Yeah, just triangular matrix. But commutation is also determined by the matrix multiplications as well. I mean the bracket relation.
Let's say the difference between this and Heisenberg
Yes.
would be, for example, what? That the only sum.
So you can also think Heisenberg is a special case of triangular as well. I mean,
Could you give an example of triangular which is not Heisenberg?
So just 3 steps: x1, x2, x3, y1, y2. This is not Heisenberg. It's a dimension 6, but triangular.
Okay, let me see.
So now I will write. satisfies transversal condition. So G is a real algebra. Yeah, yes. So G is the generators. And this one is just span of generators. And the range of element math. This one is called centralizer. So here the centralizer is the collection of all elements in G, and it does commute to S.
Generator plus what?
Generated plus the range of adjoint map. So adjoint map is it's the operator acting on the algebra. So adjoint of xy is just x comma, bracket x comma. Range of
So generators, and then you say what operations now is plus what is.
so as a vector space,
Yes,
you can think like the set there will be set of generators.
yes, and
And
then,
then span of generators
yes,
plus the range of adjoint map.
what is this plus?
I mean, as a vector space, some
Vector space was adding, so these are operations.
yeah, but it's a range of adjoint map.
Range, but first this plus, what is this plus? Just adding that. When you are defining now an element, or you are defining a set of elements.
So-
Generators is a set of elements, and then what is this class?
So this is a sub-algebra, this is sub-algebra, and everything is a sub-algebra.
The sub-algebra with these two operations, plus, and I think maybe it's G belongs to.
No, G is a linear.
This is a real algebra.
Yeah, G is a real algebra. Yeah. So real algebra
which is
written
what?
as a sum of the elements in here.
Oh,
here, and
yes,
here.
okay, so these are operations. Yes, between the algebra.
Between real algebras, yes.
Because it's defining any algebra, but how is this? And now we are going to define the constants.
Yeah, now I define the G satisfies transversality condition.
If G is of the form.
Yeah. If G satisfies a certain form.
Okay, but when you say generators of.
So generators for the real algebras. So if you consider the real algebra, then there are elements in the first level. And then here, this span means just linear combinations for
Yes.
elements in the generator.
And then,
First level.
because when you say generator, it seems that it's going to generate everything, right?
No, but we will not use the breaking relation here. That's why I wrote there's a span. It's not breaking.
It's only linear.
It's just a linear span. Yes.
Linear span of generators that they are generating with respect to bracket.
It's
And-
not breaking. It's not breaking.
And what is this class? And
It's okay. I will just draw one. So I
However, these elements are in the generators.
And I will choose some specific x. And then range of x will be, so we can find x and x2 or x and xy, they are inside of
And this,
so basically we will y.
this is the meaning of the range of elements.
So given x, we will take a bracket with other elements, then it will generate other elements. And some elements will be
Contained in the range of algebraic map. So this is the region.
so I will explain. So there's some elements with the bracket generated by x3 and xn, let's see. This may not be inside of
X. This is what I mean. So there can be some exceptions in general important algebra structures. So we have to assign some special conditions on the algebra levels. And on certain algebra, then we can find the speed of decay or ergodic difference between time and space averages. So actually this condition includes the triangular and quasi-abelian case, but it's a little bit bigger than these two previous examples.
Is it easy also to give the condition on the other side, on the side of the matrices, or the side of the group? I mean,
Yes,
now
yes,
this is
yes,
the
yes.
condition the near, right?
Yes.
But if you want to give the condition on the group,
I mean, I think it's also equivalent.
it's equivalent, but just how will it look?
How does it look? So, I think it would be better to think in some dynamical way.
Okay.
So, given some n, consider some determinant of the flow. So, given the flow, we will consider determinants. And this range of this part is the image. It's not the image, the difference. So we start from x, and we will consider n1, and then we want to find the difference between, I mean, more or less displacement between x and this return, close return to some cross section. But in this case, the cross section is very large. It's not one dimension. It's a very higher dimension. So, for the centralized condition, it always commutes with the x. And we also chose x as a generator for the flow. So it always commutes with the flow. So we can just exclude that part. I mean, we will not care because it will not affect the determinant of the flow. So this part is actually important. So if there exists some dimension that is not included in the range of Algebraic map, then we cannot control in the displacement of the first determinant. This is how we can see.
Wait, so transversality is
Yes.
what? Is the fact that we have this return map and
So transversality is,
I mean, this is more or less general conditions for the return maps. So we have return maps, and we will consider displacement difference between
Okay, and what will be the condition?
sorry.
And the condition on the displacement is, or the, you see what I'm asking? I'm asking, what is the condition?
I think I don't get your question. But what I want to say is, the condition on the layers.
If I understood correctly, you gave the definition of G which satisfies a transversality condition if it's of a certain form.
Yes.
Now in the group,
Yeah.
the group, I don't know who will, it's an element in the group that will have this transversality condition if
No, it's not element. The whole group makes
it has the transversality condition if.
But for that part, I don't know how to write. You may just exponentiate this condition.
Okay, so there is no.
There's no.
I see.
Because it's more convenient to handle the algebra. Because
Okay,
for the
okay.
group, we have a commutator and it's not convenient.
Right.
Yeah. But actually, that condition implies in dynamical way we can think in this way. So range of adjoint map is more or less this displacement of the term.
I see.
So now you can see here. Let's say the F somewhere straight. And take this side. And inside the distribution. Yes. Plus epsilon 4. So here Sm of k is a polynomial. Here also k inside. This Sm of k can be written actually explicitly by depending on the structure of the algebra. So we saw in the triangular case and quasi-abelian case, but there can be some other structures inside of transfer satisfies transversality condition. And then we can also find some exponent. So this is the main theorem.
Is it surprising that it's almost everywhere and not everywhere?
It should be everywhere, yes, but this is actually conjecture. I mean, we believe it should be every x, but our technology is very limited. And we believe so far we can only obtain some limited results. So for example, step 3 case. So for step 3 case for the quasi-abelian and the triangular. And under certain type of Prefontaine conditions, we can obtain for all. So now, I want to some state, some sketch of the proof. But before that, I want to find what is the homological equations. So homological equations, this is defined in such way, or in the map case, and also define u. So given data f, we want to find some solutions satisfies these following relations. So we will consider the flow versions, and here x means the lead derivative. So it means the infinitesimal changes along the x directions. And so d is so embedded distributions means the d of xu is equal to 0. So along the x directions, there is no changes. And then now we can see from this homological equation, embedded distribution is actually obstructions for solving these equations. So if you take d, then d of xu is always equal to 0. So that means it is necessary to assume d of f is equal to 0. So we can now see some examples for the torus. No, before the first I want to see something. So for the Nilflows case, so for Nilflows, okay, many data. For homological equations. And also there exists satisfies some differential conditions. So here on the right axis is two function. This means given flow, we can always take projected flow on the base torus. And the frequency of the base torus satisfies reflecting conditions. So given flow, we can project on the torus, and then if it satisfies the irrational condition, then there exists a solutions for homological equations. Now I want to idea of torus. So if n equal to T2, then you can choose x alpha as alpha 1. So on the three-dimensional torus, we will consider the vector case in such way. Here alpha is alpha 1. And then we can solve these homological equations. And in this case, the distribution is measured. And in the integral, So, and then back to the ergodic integrals. And then we want to find the boundary of the difference between time and space divergences. But on the torus case, there is only one unique invariant distributions. So if you assume the invariant distribution is equal to 0, then this part is actually equal to 0. And then it also means there exist solutions for homological equations. That can be replaced by actually and then are using fundamental theorem of calculus. This is U. And this one is bounded by 2 over 2, 2 over t. So basically, we can solve the homological equations. So part will be controlled by some normal f. So this idea is actually called bounded estimates. And then we want to extend this idea to the general settings. So how many times do I need?
You have time, you have time. What is no S? F, no, the one below.
Yeah.
Yes, the norm of F is respect, what's the S?
Just wrote the some somewhat less norm.
It's a somewhat.
Yeah, I didn't clarify, but usually, I mean, you can also write some CS. Well, it actually depends on your Diophantine conditions.
I see.
Because if you assign some Diophantine conditions, then you lose some regularity. So, but now the difference is for the Heisenberg case. For the Heisenberg case, as you just saw, there are infinitely many obstructions. So just assuming the zero integral is not sufficient. So yeah, I just want to give some sketch of it. Here is the renormalization. So basically, so we can consider the orbits. Then by change of variable, we can write by change of variable, we can actually divide both integrals with the scale view. So think like this way from starting x, then we can consider the flow along the flow, and then after change of variable, then we will have some shorter length. So we will identify this one. I will just write this one as a time averages, and then we can decompose this one as a invariant distributions and this remainder part. And also we can write some invariant distributions and the remainder part. But actually from this equality we can see B plus R is actually same as dt plus RT. So the main purpose of renormalization is the following. So given ergodic integral, we want to decompose with invariant distributions and its remainder part. But for the remainder part, actually we can return to this boundary estimate type. So it is more or less very good to and it's very nice to control the remainder part. So let's start. The length of the curve will be shortened, and then we will decompose. And then for this part, will be decomposed again for different time. I mean, we will make it shorter, and then decompose with invariant distribution and remainders. And then we repeat this process. And then these invariant distributions will be now for the length 1. And then there will be some remainders. But for these remainders, we more or less follow the boundary estimate. So it can be controlled. So this part will be more or less 1 over t. I mean, I didn't explain every step, but I just want to tell the idea. And this one is like D sharp. And D sharp is equal minus T over 2. So, and then we can take T over T, and then from this part we can recover T to the 1/2. But for the low part, as Felix mentioned, we will use some geophysical conditions. So some type of low probability. So if that part gives some conditions for the frequency, we will give some logarithm bound. But unfortunately, the same argument doesn't work on the general nilmanifold. So for the Heisenberg case, this renormalization is very nice. The reason is we have x, y, and z. We have only 3 elements, and one element is actually inside of the center. So we can rescale by into the t, but the other direction is into the negative t. And then center doesn't change. So more or less it's very rigid. But in general case, if you have xy1, y2, okay, if you extend x direction by into the t, and for other directions, you have to decide how to rescale. And also the difference is if you rescale minus number, go to, and then so on, then the other direction there's some problems. So for example, here z is inside of center, and the yk is also inside the center. But if you repeat the commutations, then the center is not preserved. So the one main problem is we cannot use the recurrent conditions. So we can assign, instead we can assign some Diophantine coefficients on the base torus. But for other elements in from y2 to yk, we have very weak control. So this is the one main difference. So for higher structures, greater than 1. Bounded by a constant over 1/2 and W F. So I will define what is W of F. W of F is called so here omega is a tubular neighborhood. So given orbit, we will consider the tubular neighborhood of the orbit. And then we will consider all the possible type of the neighborhood along the flow. So this one is along flow. And also this omega is the size of the loop. So basically, we will consider this direction is along the flow directions, and then we will identify the neighborhood, tubular neighborhood of the orbit in the following way. So this one is just standard tubular neighborhood, but we have to consider some such type of neighborhood. So this part is actually weak. This part is actually weak. So I will write this one is S. Then this one, the side, the area, I mean the volume is S. So this integral, I mean time averages can be controlled by average weight. But the reason why we should control this part is basically we will consider the return orbits for the flows. So given this lemma, when the size of the wish is very small, then this boundary will be very deep. So we want to exclude such that part, but instead we will take the average sense. So we will take the averages side of the width. And if there's something and yes, and then this condition, yeah, and then the average width. Yeah, and for the higher step manifold, we will consider the return orbit for the slope. And when the orbit returns to itself and doesn't intersect, but when it returns closely, then this part of phenomena happens. So we want to exclude this part, but in higher step case, when orbit returns, they become closed for a very long time. So for the step 3 or Heisenberg, the control of width is very nice. It's more or less 2-dimensional or 3-dimensional. But if you go step 4, more than step 4, then this delta type stays for long. And then after for certain time, then it starts to diverge. So this is a very bad phenomenon. And then this is also a reason why we can only prove for almost all points for the x. So another reason is we only assign the Martin conditions for the base to us. So that means we cannot use the full strength over control of all other directions. So yeah, this is one big problem. So the last part, I will just write some comment. So we want to estimate these width functions. But to estimate these width functions, so basically we want to avoid. So we will define some point as a good point. We define a good point. So good point means for the time 1, it returns to the closed sections. And then after time 1, and we will go forward one more time. And then even after that, it stays closed not for long. So that is the meaning of the good point. And then also, we will find a good point. And the second part is the width part is bounded by some ergodic integrals. Type of parabolic functions. So to avoid this kind of bad estimate, we have to cut off some of the width as width part. So in this picture, I mean, when it stays closed for too long, and to avoid this, we just truncate the width of return orbits. And then the width functions will be bounded by some ergodic integrals or some cutoff functions. And then we will return to the boundary expression. Of course, some technical part inside, because we cannot use all the points. We only want to choose some good points. And then this is also a reason why we can only prove some almost all points. So yes, this is the end of the talk.
Okay.
And thank you for listening.
So thank you very much. Are there any questions? Maybe from the online? I actually have a question. You mentioned the result of Green and Tau.
Yes.
And this paper of Green and Tau, it was actually used by them in order to one part of the results where they generalize Semiredis theorem to the primes. So this kind of estimates that you give here, do they have some applications, let's say number theory?
Ah, yes, yes. You mean this is the it has applications now. So there's a I think you know the one slide. So this is the exponential sum for and then given ergodic integrals. You can find some bounds for the bound for the Dyson. I mean, this is an exponential sum, but this is only for Heisenberg. But it's only for these two cases. So actually, during the talk I mentioned for the Heisenberg case, the bound was optimal, and then it's also equivalent to say the bound of Dyson is optimal.
Ah,
yeah. But for the quasi-abelian case, this is a degree k. But for the Heisenberg case, it's degree 2 polynomial. So for the quasi-abelian is far from optimal because the bound of Dyson is, I mean, the bound for ergodic average is quite far from the bound of Dyson. Even it's not.
I don't mean there is another bound that is known for the Dyson that is.
Yes.
Ah. But wait, but for applications, you would like to, from the other side, that you will get some new bound.
You want to find new bound as well, yes, but it's difficult.
I see. All right, okay, so if there are no more questions, let's have this again. Right. So, would you like to come to lunch?